Next, we will actually use a sample data set to show how between and within worker variability is calculated. In this example, we have 6 workers with 5 measurements each. You have on the top along the horizontal axis worker 1, 2, 3, 4, 5, 6. And for each worker, we have 5 measurements, and these are referred to by the sample ID. So these are in units of parts per million. Thus, we have a data set with 30 measurements, which is a pretty large data set in occupational hygiene. In order to conduct an analysis of variance, we need to first log transform each of the data points. And so what I'm going to present first is the results of the analysis of variance or ANOVA. And after that, in a separate section, I will demonstrate how this is done in an Excel spreadsheet using ANOVA. So in this slide, what I'm showing are the 6 workers and the average exposures of each worker and the variance for each worker's measurements. So if you remember, there are 5 measurements for each worker. The column on the extreme right shows the variance, and the column titled average shows the arithmetic average of each worker, and the count refers to the number of measurements per worker. And if we cursorily look at the averages of the 6 workers, we see that the averages of the first 4 workers are similar, but the averages of the 5th and 6th workers are quite different. Now, if we carry out an analysis of variance or ANOVA of 6 workers with 5 measurements each, you will see in this output from the ANOVA several columns and 2 main rows, between group and within group. The between group and within group are terms that the ANOVA feature in Excel uses, but in our particular example, the group actually refers to a worker in this instance, because we now have 6 workers or 6 groups, and we want to find out what is the variation between group, or in this case, between workers and within workers. The second column, SS, refers to the sum of squares, and the third column, DF, refers to the degrees of freedom, and MS refers to mean squared error, and the F refers to the F statistic for our particular data set. The ANOVA also calculates a critical value of F, which is in the last column. And in the second to last column, we show the p-value, which is the difference between groups statistically significant or not. And we judge the statistical significance in this case with a p-value of 0.05. And the p-value for this data set is less than that. We are at 0.034. And therefore, we can conclude that between worker, or what ANOVA terms as between group variability, is significant. Also, we notice that the F value calculated is greater than the critical F value. So both of these lead us to conclude that between group variability is significant. As I said in the previous slide, the p-value is less than 0.05, and the F value calculated is greater than the critical F value, and therefore the between worker variability is significant. The within worker variance, or sigma W squared, is calculated as 0.24, and the between worker variance, or sigma B squared, is calculated as 0.09. And the total variance, sigma T squared, is the sum of squares of the between worker and within worker variance. And that comes out to be 0.33. And we can take the ratio of the between worker to total variance, and this turns out to be roughly 27%. And so 27% of the variability in exposures is due to differences between workers, and the rest of it is because of variance within workers. And 27% is a significant amount of variability that it affects how we interpret the results and how we might take risk management steps. The within worker geometric standard deviation is basically the exponent of the within worker standard deviation, and that comes out to be 1.63. And the geometric standard deviation of between worker variability is the exponent of the standard deviation of the between worker variation, and that comes out to be 1.35. So it's important to note here that even though the GST of the between worker variability is less than the GST of the within worker variability, we still conclude that the between worker variability is a significant contributor to the overall variability. Now we can also look at the results of our ANOVA visually and see what it all means. If we had just taken all the 6 workers and their 5 measurements each and plugged it into our IHstat Excel spreadsheet and calculated or plotted the results on a log probability plot, then the data would fall on the straight line that is shown by the solid line in the middle that is marked as all workers. And we could then calculate the geometric mean and the geometric standard deviation as we have learned how to do that. But we can also do one more thing, which is that we can plot the log probability plot for each worker, because each worker now has 5 measurements. And we see that there is a straight line corresponding to each worker's log probability plot. We further see that for workers 1, 2, 3, and 4, the straight lines are all clustered together, whereas for workers 5 and 6, those straight lines are a little bit farther away from the first cluster. And we can see that they, in fact, are significantly different, even visually, from the first 4 workers. We had also noticed this when we looked at the averages of the 6 workers, and we noticed that the average of worker 5 and 6 were significantly higher than the averages of the first 4 workers. So this visual analysis confirms what we concluded from the results of our ANOVA, that there is, in fact, significant between worker variability. And it is most likely because of worker 5 and 6. And most probably, they should not be in this group. They do not belong in this group, and they have been misclassified. One further point, the ANOVA model assumes that the within worker geometric standard deviation is the same for all workers. We had previously calculated this as 1.63. However, if we plot the exposure data for each of the workers, where a straight line is fit to the data, then the slopes of the individual lines are different from each other. And this tells us that the geometric standard deviation for each worker is different from the others. The model, on the other hand, calculates an average within worker geometric standard deviation using the data for all the workers.